Hi, this is Dr. Bricker here with some hints for homework number 6. Okay, so the first problem from chapter 25, a scalloped hammerhead shark swims at a steady speed of 1.1 meters per second with its 82 centimeter wide head perpendicular to the Earth's 58 microtesla magnetic field. And we want to know what is the magnitude of the EMF, or in other words, voltage, that's induced between the sides of the shark's head. And we want the answer in millivolts. Let's take a look at this. Okay, so as the shark swims, I just have the shark going to the right here, swims to the right. I have the Earth's magnetic field being perpendicular to it, just to illustrate how this might work. Swimming to the right, Earth's magnetic field perpendicular to that, so I just have that going into the page. So what happens is there is a magnetic force on charges. So V is this way, B is into the page. The force on positive charges is up. The force on negative charges is down. And eventually we build up an electric field then, positive, negative. So the magnetic force is up. The electric force would be down. We get to the point where those are equal to each other. And we did this in chapter 24 and chapter 25. You set those equal to each other and you arrive at this equation. The induced EMF is the speed times the magnetic field strength times the length of whatever is going through the Earth's magnetic field. So this is the hammerhead shark. Moving to the right, we develop a voltage across this part, the hammer part. And this is the magnitude of the induced EMF. So we're actually given everything here. V is given, B is given, L is given. Just make sure that you put all of these quantities in SI units. So meters per second, that's no problem. 0.82 meters, 58 to the minus 6 Teslas. So Mastering Physics is calling for the answer in millivolts. When you do this, remember you'll get the answer in volts. You'll have to convert it to millivolts. So by the way, this idea works for a hammerhead shark going through a magnetic field. It also works for an airplane going through a magnetic field. So if you're in an airplane flying through the Earth's magnetic field, you'll develop a voltage across the wings, all the way into the millivolt range, or maybe even more. And people who design airplanes have to take that into account. Okay, let's look at the next problem. Okay, so this problem has the same conceptual idea. Remember, if you need to review the concept, you can click here and review the section from the book. Okay, so in this figure, we've got a 20 centimeter long metal rod pulled along two frictionless conducting rails at a constant speed. The rails have negligible resistance, but the rod has a resistance of 0.7. So here's the rod. It's moving to the left with a certain speed. So the rod has electrons in it. They're going to experience a force. So V is this way. Magnetic field's into the page. Use the second right-hand rule to figure out the direction of the force on positive charges. So V is to the left. Magnetic field is into the page. So thumb in the direction of V, pointer finger into the page, and you'll see that the direction of the force on positive charges is down. So you get a whole bunch of positive charges here. The force on negative charges would be the opposite direction. So up here you get a whole bunch of negative charges. Same idea as the last problem. Separation of positive and negative charges will produce an electric field. The electric field would be this direction. Eventually you get to the point where the electric force and the magnetic force are equal to each other. So you develop a voltage across this. So the faster you pull it, the more voltage you develop. Okay, let's take a look at this problem. Okay, so here's the rod moving to the left. As I said, this side you get a whole bunch of positives, this side a whole bunch of negatives. That's really what a battery is. So you're going to have current flow in the rod, and the current's going to flow this direction from positive to negative. And this is a conducting material, so we actually will have current flowing this way. To figure out the amount of current that's going to flow, we'll use what we've done in this chapter along with Ohm's law. Same idea, the voltage VB times L. So we're given V, we're given the magnetic field strength. I didn't write it down here, but we're given the magnetic field strength and the length of the conducting rod. So you can get the induced voltage, use Ohm's law to figure out how much the current would be. Okay, so there's the amount of current. Another part is to figure out the magnitude of the force. So if you have current flowing from positive to negative, through the rod it's going to flow this direction. Now current flowing through a wire in a magnetic field experiences a force. So as you're pulling this to the left, there's going to be a magnetic force back to the right. So you don't get anything for free. If you're pulling this way, there's going to be a magnetic force back that way. So refer back to chapter 24, but the force is I times L times B. So again, as you pull it to the left, there's going to be a magnetic force back to the right, and here's the magnitude of it. So you'll need the current that you got from the first part, length of the rod that you're moving, times the magnetic field strength. So unfortunately, you don't get anything for free. The harder you pull it to the left, the more current flows, but at the same time, the more the magnetic force is back towards the right. Okay, let's look at the next one. Okay, so in this problem, the figure is an edge-on view of a 10-centimeter diameter loop. Okay, so you're seeing the side view of this loop. There's the magnetic field pointing to the right. Here's the loop. Now remember, the area vector of the loop is defined as being perpendicular to the area of the loop. So the area vector of the loop is right here along sort of the axis of the loop. Okay, so we've got a 10-centimeter diameter circular loop rotating in a uniform magnetic field, and the magnetic field strength is given. And we want to know, what is the magnetic flux when this angle is 0? Okay, so for that to be 0, you'd have to rotate the loop so it's standing like this. So when theta is 0, all of the magnetic field is going through the area of the loop. Part B is what happens when you're at 30 degrees. Okay, so you can see, here's the magnetic field strength. When you have some angle here, the amount going through there is less. 60 degrees, even less. 90 degrees, nothing's going through it. Okay, so let's take a look at this problem. Okay, so here's the loop. Here's the area vector as I described it. So magnetic flux is B times A times the cosine of the angle between B and A. So if B is to the right, the area vector is perpendicular to the area of the loop. Here's the angle between it. So when theta is 0, that's when the flux is a maximum. So this will come out in Tesla meters squared, and a Tesla meter squared is a Weber. Okay, so so how do you get the area? Well, they give you the dimension of the loop, so you can get the area of the loop. So B is actually given. These different thetas are given. Just remember, it's the area of a circle, which is pi r squared. So just be careful with the units. Make sure it comes out in Tesla meters squared. Okay? And then they don't ask for this one, but when theta is 90 degrees, that's when the loop is laying flat here, and no magnetic field is going through it when it's flat. Okay, let's look at the next one. So we are given 13 meter of thin wire that you form into a circular coil with 50 turns. If the coil is placed with its axis parallel to 0.19 magnetic field, okay, so we know the magnetic field strength, we know how many turns we have, and we know the dimension of this. What is the flux through the coil? Okay, so similar to the last problem, we're assuming it's a circular coil, so you can figure out you know, the area of one of the loops. So it's 13 meters of thin wire. You'll have to figure out the circumference of just one of those loops, right? So 2 pi r times n, where n is the amount of loops, would have to be 13 meters. So let's take a look at this one. Okay, so we've got a total of 13 meters of wire, and we're going to form this into a loop, but we're forming 50 loops. So to get the flux, we're going to have to figure out the area of each loop, but we don't know the size of each loop. But we can get that because we know if you take the circumference of one of the loops, right? The circumference of a circle is 2 pi r. The circumference of one of the loops, and we've got 50 total loops. So 50 times 2 pi r, this has to give us 13 meters. So once you realize that this is the circumference of one of the loops, the distance around one of the loops, times the amount of loops that is given, 50, that has to be 13 meters. So then you can figure out the radius of one of the loops. Once you have the radius of one of the loops, you can use that number to get the area of one of the loops. So pi r squared. Just be careful with the units again. This will come out in meters, so you shouldn't have any problem. Here's the area of one of the loops. Once you have the area of one of the loops, then you can go back to our magnetic flux formula. So we want the total flux. So 50 times the magnetic field strength times the area, which you just found, times the cosine of the angle between B and A. But remember, they're telling you that the axis of the loop, this is the area vector of the loop, it's lined up with the magnetic field strength. So B. Okay, so the cosine of 0. Excellent. Let's look at the next one. Okay, so in this one, a magnet and coil are oriented as shown. The magnet is moved rapidly into the coil. So here's the magnet moving into the coil, held stationary for a short time, then rapidly pulled back out. Excellent. So there's a changing magnetic flux. When you move the magnet towards it, more and more magnetic field lines go through there. So as we know with Faraday's law, more and more magnetic field lines, that means there's a changing magnetic field strength, changing magnetic flux. When there is a changing magnetic flux, that's when we have an induced EMF. So let's take a look at this one. Okay, so here's the magnet being moved towards here. So remember, as we look down on this, magnetic field lines come out of the north and go back into the south. So if you're looking at this loop, initially we're like this, there's some magnetic field lines going through, but as you move it closer, there's more. So this is Lenz's law that we're using here. So magnetic field lines are leaving the north side of the magnet, going through here. So what you see are magnetic field lines going through it. So you see the X's, and as you move it closer, you get more and more X's. Now remember, Lenz's law says that the induced current is going to flow in such a way to try to get us back to this initial situation. So current is going to have to flow this way. And then its own magnetic field, so use the right-hand rule here, current's going this way, its magnetic field would be out at you, trying to kill off that increase. So if current is flowing this way, that means it's the induced voltage is positive. So initially you have something like this, and then for a short amount of time where no current is flowing, you don't have anything. And then when you pull the magnet back out, you could almost just guess that it's going to do the opposite, but let's look at it with Lenz's law. So when you're pulling the magnet back out, we're going from something to something less. Nature likes to be in this situation. So the induced current is going to flow this way, and then its own magnetic field into the page, trying to get us back to that situation. So if current then flows the other direction, that's where it's defined to be negative here. Okay, so Lenz's law problem. Let's look at the next one. So we have a 1300 turn coil of wire. We know the diameter is given there, 2.3 centimeters. Just be careful. You're going to need to put that into meters. Is in a magnetic field that drops from 0.11 to 0 in 11 milliseconds. So 11 times 10 to the minus third second. The axis of the coil is parallel to the field. And you can take a look at this video tutor solution here to help you out. What is the induced EMF in the coil? Okay, so it's a Faraday's law problem. There's a changing magnetic field. when there's a changing magnetic field, there's going to be an induced EMF. So we really just want the magnitude of the induced EMF here. Let's take a look at this. Okay, so I've got 1,300 turns. Here's the diameter. Make sure you put it into meters. Initially, the magnetic field is at 0.11. That's my notation here. B initial. So B final is 0. And this happens in a certain amount of time, 11 milliseconds. Again, be careful. So here's Faraday's law, the induced EMF minus N, change in flux divided by the change in time. So magnetic flux, again, is made up of B times A times the cosine of the angle between those. So one of those quantities has to change. And in this problem, it's the magnetic field that's actually changing. We'll have to do a little bit of work to get the area, but you can do that. It's the area of a circle. They give you the diameter. Just be careful if you want to use the radius form of that formula. Here's what the picture might look like. Here's the loop. Magnetic field strength is going through it. The area vector is perpendicular to the loop. That's the area. So they're lined up with each other. So theta is 0. Cosine of 0 is 0. Okay, so here's Faraday's law again. Minus N, that's the number of loops. The area, which you'll have to find. And then the part that's changing is the magnetic field strength. Delta B over delta T. And you can get that because you know the initial and the final. So you could figure out the changing magnetic field, the amount of time is given. So put that all together to get the induced EMF. Okay, excellent. And we just want the magnitude. This would come out to be negative anyway, but we just want the magnitude. Okay, let's look at the next one. Okay, so 2519, patients undergoing an MRI occasionally report seeing flashes of light. Some practitioners assume that this results from electric stimulation of the eye by the EMF induced by a rapidly changing field of an MRI solenoid. So the solenoid has a changing magnetic field. A changing magnetic field induces a voltage, and there's charge carrying material in your eye, so you can stimulate the retina that way. We can do a quick calculation to see if this is a reasonable assumption. So the human eyeball has a diameter of 25 millimeters. Okay, so we can calculate the area of the eyeball. Rapid changes in MRI solenoid can produce rapid changes in the magnetic field of something like 60 teslas per second. So that's a lot. You can take a look at the video tutor solution here as well. So we want to figure out what EMF would be induced in the eye. So assuming that the eye is a conducting loop, and we can figure out the area, we know how fast the magnetic field's changing, we can calculate the induced EMF, and then we can compare that to, in part B, this action potential of 15 millivolts. Is this induced EMF enough to actually make this happen? All right, let's take a look at this. So really similar to the last problem. Here's the diameter, and we're going to assume that the eye is round even though it's not, but for sake of the calculation we will. So you can figure out the area of the eye, right? Just assuming it's a circle. The delta B over delta T in this problem is actually given. In the last problem you had to calculate it, given the initial and final magnetic field strength. Okay, and we're assuming again that the magnetic field is lined up with the area vector, so the cosine of 0 would be 0. Whoops. So we have the induced EMF, this is Faraday's law, minus N delta B over delta T, and then don't forget to multiply it by the area. And then we have the cosine of 0, which is 1, so I didn't write that part. So the eyeball, we're just assuming N is equal to 1. Delta B over delta T is given in the problem. And again, the area you'll have to calculate, assuming it's circular. Right? Area pi r squared. All right, excellent. And we just want the magnitude of this. Okay, really similar to the last one, changing magnetic field through a loop. You can model it as same thing as the changing magnetic field in your eye and calculate what this voltage would be. And then compare it to the 15 millivolt action potential. Okay, be careful. I'm not sure if they want the answer in millivolts or volts. So take that into account when you enter your answer. Let's look at the next one. Okay, we did something similar to this actually in the lab. We had a solenoid inside another solenoid. In this one, it's just a solenoid inside of a loop. But the idea here is the solenoid produces a magnetic field. Now, if this solenoid's magnetic field is changing, it's going to induce a voltage in this outer loop. In the lab, this outer loop was actually another solenoid. We had two solenoids nested. Okay, so a solenoid passes through the center of a wire loop. Here's the solenoid. Here's the loop. As shown, the solenoid has 1,200 turns, a diameter of 2 centimeters, and is 7.5 centimeters long. So be careful with all these units. We need to think about SI units. The resistance of the loop is 0.032 ohms. If the current in the solenoid decreases by 1.4 amps in 50 milliseconds, what is the induced current in the loop? Okay, so from chapter 24, if you have a solenoid and you have current flowing through it, it produces a magnetic field. So we're going to have to use some information looking back at chapter 24. We can calculate the magnetic field because of a solenoid. And we see that the current increases, so the magnetic field strength is going to increase. That's what's being produced by the solenoid. But at the same time, here is a conducting loop. There's a changing magnetic field because the magnetic field of the solenoid is changing going through this loop, so there's going to be a voltage induced there. Okay, let's put this all together. Okay, so here's my picture. This size of the solenoid is given. Now remember, when we calculated the magnetic field strength due to a solenoid, this didn't matter. This comes into play when we're trying to calculate the flux going through this loop, and you'll see how in just a minute. 1,200 turns, 0.075 meters long. I put this into SI units. Here's the resistance. And here's the rate of change of the current. Okay, so for now, for a solenoid, the magnetic field was mu0 I N over L. I'll just write it like that. So mu0 is a constant. You can look it up, 1.26 to the minus 6th. Current, number of turns, length. So a changing magnetic field is going to be mu0, I'll write it like this, N delta I over the length. So magnetic field produced by the solenoid would be this. That's from chapter 24. Now if it's changing, the part that's changing is the current. So a changing current produces a changing magnetic field. So they give you the amount of current that changes. It's 1.4. And that happened in 50 milliseconds. So 50 to the minus 3rd second. You can find out the rate of change of current right away. Okay, so I want to keep it like this. This is the change of the current, 1.4 amps. This is the amount of time that it takes, 50 milliseconds. So 50 times 10 to the minus 3rd seconds. Okay, so we've got a changing magnetic field because the solenoid is changing. We want to know how much voltage is induced in this outer ring. That's where we could, again, use Faraday's law. Okay, so this is for the ring. Now, the amount of loops in the ring is just one. It's just one loop. The area of where the flux is contained is just with the solenoid. So that would be pi r1 squared. So again, this is the amount of turns of the outer loop. This is the amount of area that's actually being penetrated by the magnetic field. That's why it's pi r1 squared. I mean, we're talking about this loop r2, but where the flux is contained is just here, this pi r1. So n, this is the area, and then we want to know the changing magnetic field divided by the changing time. Okay, so to get the delta B part, we have this formula. Right, that's how much the magnetic field changes. And then the delta T part is given in the problem. Okay, so it's a pretty complex problem, actually. It's the basis of a transformer. But putting it all together, that's what we have. So amount of turns in this loop, just one. Here's the area of that loop that's being actually penetrated, pi r1 squared. And then here's the part that's changing going through that loop, delta B over delta T. It's just, in this problem, it's more complicated because you have to calculate the delta B for the solenoid. But you can do that. Put everything together, look up mu0. This is the amount of turns of the solenoid, 1200. Here's the length of the solenoid, 0.075, etc. Okay, it's a good problem. Have some fun with it. All right, let's look at the next one. Okay, so now we move into some wave type problems, electromagnetic waves. A typical helium neon laser found in a supermarket checkout scanner emits 633 nanometer wavelength light in a 1.3 millimeter diameter beam with the power of 1.1 milliwatts. What is the amplitude of the oscillating electric field? And then what's the amplitude of the oscillating magnetic field? All right, let's take a look at this. Okay, so we know that a changing magnetic field produces an electric field, and a changing electric field produces a magnetic field. But how do we know that that information comes to us? Let me give you a scenario where this would be possible. So say you had a situation like this. It's a conductor that's positive and negative. This is somehow connected to a battery. So this is positive, that's negative. So what if you quickly reverse the polarity of the battery? So by doing that, I mean, what if you could do something where this changes around, that this is negative and this is positive? So you could do that somehow. You can figure out a way to switch that around. So now we've got a changing electric field. The electric field was this way. Now the electric field is this way, right, from positive to negative. So a changing electric field produces a magnetic field. So a magnetic field wasn't there. Now we have a magnetic field. So you have a changing magnetic field. And then a changing magnetic field produces an electric field. And so on and so on and so on. So when that happens, that's how an electromagnetic wave is built. So this is supposed to just be, not actually moving here. That's just in one plane. So you've got a changing electric field. The electric field was pointing this way, and then quickly, in the same space, it's pointing this way. Changing electric field produces a magnetic field. Now you're over here. When do you actually get that information? So that's your eye. It takes some time for this wave to actually get to you. So a changing electric field produces a changing magnetic field, and then a changing magnetic field produces a changing electric field. So if you're over here and you're measuring the electric field here, when does that electric field make it all the way over to here? Right? Because it's just right here, and you're measuring it over here. So how does that actually happen? Well, it takes some time for the electric field that's associated with this to get over to you. It turns out it travels at the speed of light. So when you read through the last part of chapter 25, you'll see that. So here's an electric field that's changing. It's producing a magnetic field that's changing. And then the changing magnetic field produces an electric field, and so on and so on. And that wave eventually travels to you. That's what an electromagnetic wave is. Okay, so with that in mind, let's take a look at this problem. So it's a supermarket laser. Here's the wavelength, so lambda, 633 nanometers. That's just describing the laser. So here's the beam traveling this way. We know the diameter of the beam, 1.3 to the minus third. Be careful of the units again. So the radius would be half that much. And we're given the power of this laser, 1.1 milliwatts, so to the minus third watts. And as a reminder, a watt is a joule per second. So we want to figure out the electric field part and the magnetic field part of this wave. So the intensity is the power divided by the area. We also know that the intensity, and when you read through the chapter and watch the videos, you'll see this, it's 1/2 epsilon naught. This is what we had before, 8.85 to the minus 12th, times the electric field part. So be careful with this formula. Know what everything means. This is a constant, epsilon naught, that we've seen before with electricity. This is the electric field amplitude. Okay, E sub 0. So in this problem, the power is given to you, 1.1 watts. Now the area is the area associated with this beam. So it's the area of the circle here. So area pi r squared. Okay, so you can calculate, you're given the power, you can calculate the area. It looks like there's a lot to this formula that you don't know, but it turns out that there's not really, because this is 1/2, it's just a number, epsilon naught is a constant. So power given, calculate the area, and then the only thing that you don't know here is the electric field strength. So you'll have to do a little bit of algebra and solve for that. Now there's a couple ways of getting the magnetic field strength. Probably the easiest way is to look at the relationship between the electric field amplitude and the magnetic field amplitude. So E sub 0 divided by B sub 0 gives us C, and C is the speed of light. So if you know the electric field part, which you'll get that from the first part, you can calculate the magnetic field part. So when you know the electric field part, you can really easily calculate the magnetic field part. So from this formula, the magnetic field part turns out to be the electric field part divided by the speed of light. Okay? On the other hand, if you just wanted to go through power, area, 1/2, speed of light, mu 0, which we know that too, times the magnetic field part, you could do that as well. This is just more straightforward, I would say. So part A, use this to calculate the electric field strength. And then part B, this is the easiest route to calculate the magnetic field strength. Now, if you want to for fun, you could do it the other way. P over the area, 1/2 C epsilon naught magnetic field strength part. And you'll see you'll get the same answer. All right, let's look at the next one. Okay, so biologists use optical tweezers to manipulate micron-sized objects with a beam of light. In this technique, a laser beam is focused to a very small diameter spot. Because small particles are attracted to regions of high light intensity, the focused beam can be used to grab onto particles. So essentially you shine a focused beam, small particles are attracted to this light. Okay, so that's how they're used to grab on, because of that attraction. And once that happens, you can manipulate the particles for whatever purpose you want. In one experiment, a 20 milliwatt, okay, be careful, milliwatt to the -3rd watts, laser is focused to a spot that has a really small diameter, so 0.82 micrometers, so 0.82 to the -6 meters. And we want to know what's the intensity of light in the spot, and then what's the electric field strength. Okay, so similar to the last problem, but let's just take a quick look at it. Okay, so the power is given. It's a laser again, so it's got this shape. Here's the area, pi r squared. So now the intensity is the power divided by the area. The power is given. The area you'll have to calculate from pi r squared. So it's really similar to what we did before. So just a word about this idea of intensity. Let me pretend that I have a light bulb here. That's not a very good light bulb picture. So here's a light bulb, and it's 100 watts. So regardless of where I put my hands, this is 100 watts. If I move my hands close to the light bulb, the intensity is great, because all that power is over a smaller area. If I take my hands and move them farther away, it's the same light bulb, so it's got the same power, but the intensity of that I'm feeling farther away is less. So power doesn't change, the intensity changes depending on what area is receiving that power. So if I'm really close, it's a really small area and it's intense. If I'm farther away, same power, but that power is being distributed over a greater area, so the intensity is less. Okay, so first part, just like the last problem. And then to get the electric field strength, do what we did on the last problem. We use this formula that the intensity was 1/2 epsilon naught. You'll have to look up that constant, and then the electric field part squared. So 2I epsilon naught, square root of that will give you the electric field part. Okay, let's look at the last couple of problems. Okay, so in this one, only 10% of the intensity of polarized light wave passes through a polarizing filter. We want to know what's the angle between the electric field and the axis of the filter. Okay, so let's take a look at this. Okay, so first just a comment about what unpolarized light is. Unpolarized light, the electric field part is going in all different random directions. So again, make sure that you're reading through the chapter, watching the videos. This is unpolarized. Now, if you send it through a filter, you could polarize it. So polarizing means that the electric field is just going in one direction. So you put this through a filter, it comes out, it's just polarized it's polarized. That means it only has one direction. This has an infinite amount of different directions. So by definition, it's the direction of the electric field that determines how it's polarized. So these are the electric field parts, all different random directions. This is unpolarized. You put it through a filter, it becomes polarized. So going through a filter, this would be polarized, just in one direction. Whoops. Maybe like this. So in this problem, you're taking polarized light, which is something like this, just having one direction. You put it through a filter, and you only get 10% out. So 0.1 of the incident wave is actually transmitted through. We want to figure out the angle between the incident light and the transmitted light. I just included a couple of equations here. They're asking for the intensity, not the electric field part. So the electric field transmitted part is equal to the electric field incident part, and then the cosine of the angle between the filter and the electric field. This is what we'll use for this problem, though. So the transmitted part is equal to the incident part, and then the cosine squared of the angle between those. Okay, they don't actually tell us how much is incident, how much is transmitted. They just tell us that 0.1 is transmitted. So let me do a little bit of algebra here. So I transmitted divided by I incident is the cosine squared of theta. This is what they're telling me is 0.1. The ratio of transmitted to incident. They're telling me in the problem that that is 0.1. Okay? So read through the problem again, but this is what they're saying, 10% is transmitted, so the ratio of transmitted to incident is 0.1. Okay, and then it's just a little bit of algebra. Take the square root of both sides, and then take the inverse cosine of both sides to get that angle. Okay, let's take a look at the next one. A radio antenna broadcasts at 1 megahertz, that's the frequency, with a power of 30 kilowatts, so 30 times 10 to the 3 watts. Assume the radiation is emitted uniformly in all directions. What is the intensity 25 kilometers from the antenna? And what is the electric field amplitude at that distance? Okay, excellent. Let's look at this. So here's the radio transmitting station, transmitting in all different directions. Now this is different from the laser one. With the laser problems that we've been doing, here's the wave. It's just going through this surface area, pi r squared. So it's going in just in one direction like this. And then it's hitting a certain surface area. This was for a laser that we saw before. Here it's a transmitting tower going in all different directions. So it's this is just the area of a circle that we're hitting. This wave is hitting like the inside of a sphere. So the area here is the area of a sphere. So I mean, you're just looking at a piece of paper. It looks like it's going in one direction, but it's going in 3 dimensions. So pretend like this tower is in the middle of a sphere. And given the frequency and the power, we want to know the intensity out here. So similar to what we've done, the only difference is it's the area that's being hit by this wave. So the power is given, 30 kilowatts. Now it's the area of a sphere. So pi r squared, 4 pi r squared. So the power is given, 4 pi r squared. So, you know, the area of a sphere would be 4 pi r squared. The r here is the distance from the tower to wherever we are at. So you can get the intensity that way. And then just like we did in the previous problems, the electric field strength comes from this intensity. So we need the intensity from the first part. This would be 1/2 epsilon naught, that's just a constant, electric field amplitude squared. So again, you'll have to do a little bit of algebra. So be very careful with this. I mean, this is epsilon naught. Know what this is. Remember, that's the 8.85 to the minus 12th number. This is the electric field amplitude, E field. Okay, and then this is the intensity. I know it can be confusing. We just did current, which also is measured in I, but in this context, I means intensity. Okay, email me if you have any questions, and I'll talk to you soon.